In section 2.3, we will discuss electric potential, and the very first thing is that we will introduce electric potential in section 2.3.1. The very first question that comes into mind that when we are having the electric field, then what's the need of defining another physical quantity? What's the need of defining electric potential when we are having the electric field? So here is the situation that, for example, if we are having two positive charges, or let me consider first that this is a region, and in this region, let's say this is an arbitrary region, and in this region we are having no charge, that is, the source charge is equal to 0. Then this will tell us, from Coulomb's law we came to know about this thing, that electric field will be 0 in that region as the source charges are equal to 0. Now if, for example, we are having two positive charges, like we are having a positive charge here and a positive charge here, and both are of the same magnitude, Q and Q, then what is the electric field at the center? Now the field at the center is E equal to 0. The electric field at the center is equal to 0. Now let's look here and here. These are two different scenarios. Like, for example, we are having this region here, any arbitrary region in which we are having this situation. Now look here. Here the electric field is 0 by magnitude. Like, the magnitude is such that the electric field is equal to 0. And here the electric field is 0 by magnitude, but not due to the source charges. Here the electric field is 0 because there are no source charges. Here are the source charges, but the electric field is 0. Now these two things are 0. This we say that this is due to the source and this is due to the geometry. So the two equal to 0, how we will tell the mathematics that this equal to 0 is different from this equal to 0. And there comes the need that this one is coming out to be 0 due to the reason that the two electric fields are cancelling each other due to their vectorial nature. So the concept of electric potential comes here, that we need something that depends on, not depend on the vector form, or is not supposed to be vector in nature, but to be a scalar. And here V will not be equal to 0, but here V is equal to 0 as well. So the vectorial nature was giving us a problem there, and it was giving us 0. Then we got rid of this thing by introducing its scalar counterpart, and that's why we can easily differentiate that here it's a different scenario and over there it's a different scenario. And there is a need of defining electric potential. Now we know that when we talk of electric field, then electric field is not an ordinary vector, an ordinary function, but it's a special kind of function such that its cross is del cross, its curl will always be equal to 0 as long as we are in the regime of electrostatics. I'm not talking of the electrodynamics, because over there the curl of E is non-zero, as we know in Faraday's law of electromagnetic induction. the Faraday's law, del cross E equal minus curly P by curly T. So here, as long as we are here, then we in electrostatics, so we will have the curl of E equal to 0, means it is not possible to have electric field like this, for example, like y and the x unit vector. Because for this kind of vector, del cross E is non-zero. You can check this thing. This is non-zero. So there is no such charges or combination of charges which can produce such a field. So it's a special kind of a function or a field which has its curl equal to 0. And now we define the electric field, that this thing we came to know from here, that when del cross E is equal to 0, then it demands that this E is the result of the gradient of something which we have studied in chapter 1st. So I can define that if I'm like, for example, the endpoint does matter when the closed loop integral of this thing is equal to 0, like the earlier we did this thing, that E dot dl is equal to 0 around a closed path. So it doesn't matter, while moving from A to point B, you go this path or you go this path, it doesn't matter. Only the endpoints does matter, and such a field we call a conservative field. And if it would not be a conservative field, then we will have the closed loop integral non-equal to 0. So here we define the electric potential is V of R, and this is defined as the 3 lines is for the defined as we are defining it from an arbitrary point O is written in this form, to R, and this is E dot dl. So this is E dot dl. And now this is, I have earlier in the earlier lecture I have told you that this is actually the work done on a unit charge. Now why we are having a minus sign here, I will explain all these things. Like for example, we are having a positive charge here, and over here this is the vicinity in which this charge is having its impact, and like the impact is still infinity, and this is the region that I have enclosed here, and let's say this is our point which I'm calling as point O, which I'm considering at infinity. Now keep in mind one thing, infinity never means you move very far. When you go out of the influence of that thing, then it is infinity for it. So let's say this is point O, and I'm moving a test charge plus Q here, or let's say call this Q naught, and here I'm having a source charge Q. Then when I am moving this charge from this point toward this charge, I'm doing some work, and that work is converting, that work is being stored as energy in this system. But think of this thing, I'm coming from infinity towards the charge, and I'm doing work against the charge. If I will consider the electric field, then the electric field is doing work in the opposite direction. It's going in the opposite direction, and I'm going from there to here. So that's why if it is the work of the field, then it is with plus sign, and the minus sign means that it is the work which is done against this one, and we call this thing is electric potential. We define this thing as electric potential. Another thing to note here, that electric potential is not a physical quantity. Electric potential, or sometimes it is called as absolute electric potential, it is not a physical quantity, because physical quantity means we can measure it. The electric potential we cannot measure. We can measure the potential difference and not the electric potential, because we can't specify what is this point from where it is coming in, where this infinity point is. So this is a single value thing, and we cannot term it is a measurable thing or a physical quantity. The thing that we can measure is called a potential difference. And the potential difference, let's say on the way, I'm having this is point A, this is point A, and this is point B. These are the 2 points. And now I know that the potential, the value of the electric potential at A point is VA, and the value of electric potential at this point is VB. And then I can write that VB minus VA is equal to, now I can write here that minus, now VB means from this infinity point O, I will reach the B point, and then this is E dot dl. And then minus here, and another minus means this minus, it is this one. And then what is VA? VA is again with minus sign, and then integral from point O to point A, and this is E dot dl. Like while moving from here, I'm going independently to point B, and then from point O to point A, and it will be equal to this. And this thing I can write that this is equal to, this will become plus, and I can write this one is minus integral from O to B E dot dl plus integral from O to A point E dot dl. Now what about here, this thing I can combine now. Like I can write that this is equal, this thing is equal to, I can combine and I can write this is from minus from point O to point B E dot dl. And if I reverse these 2 points, then minus sign will occur, and this is from point A to O and E dot dl. Reversing the limits of the integral will be equal to this. And now I can write, if I write this one earlier and this one later, then this is equal to minus A to O and E dot dl minus O to B and E dot dl. and this thing simply is equal to minus. Now from A to O and from O to B, so this I can write from A to B in a combined form, and E dot dl. So this is this side that I can write. Now what about this side? We know that what is VB minus VA, the theorem of the fundamental theorem of gradient, we have said this thing, that integral from A to B gradient of t dot dl is equal to the value of t at the endpoints, ta minus tb, tb minus ta here. So this is the value of this gradient t dot dl. So incorporating this result, this is the fundamental theorem of gradient. So we will incorporate this result here, and this is giving us, I can write for Vt here, so it means that this thing is equal to from A to B and gradient of V dot dl. This is equal to minus E dot dl. And now from here, the endpoints are the same, and it's a fractional length, the smallest, the minimum length possible, and this is E dot dl. So the same limits, the same length element, so the integrand will cancel out here, and I can simply write from here that gradient of V is equal to minus E, or this I can write is E equals minus gradient of V. And this is the result we were behind, that when the curl of E is equal to 0, means the lines are not curling, they are going straight. And when they are going straight, it means they are diverging. When they are diverging, then they are going in straight line, they are not curling at all. It means that electric field is the result of gradient, because gradient is the maximal change in a given direction, and I can write that electric field is the negative gradient of electric potential. So these two things I can now summarize here, that del cross E equal to 0 implies that E is minus gradient of V. Now some comments on the electric potential. The very first thing is that is the electric potential, or simply we call it potential, is the electric potential and versus the potential energy, are these two the same thing? So they are completely different things. They are not the same. Electric potential has nothing to do with the potential energy. Keep in mind, electric potential is the work done on a unit charge. So dimensionally, they are different things, although their names resembles, but they are completely different thing. I have earlier discussed that the advantage of going to electric potential is that, for example, we are having a meter, and that meter is measuring only the electric field here in this room. So if I will be having that meter, and there are, for example, charges on one wall and on the other wall, and I'm checking through the meter and I'm going here at the center, then I will see that there is zero electric field. The meter will be reading zero electric field, and then I will conclude that there are no charges. But this conclusion will not be correct, because I will have to keep in mind the vectorial nature of the electric field. My meter should have also another option to check the voltage as well, to check the potential as well. And when it is on the potential, then I'm moving and I will feel that the potential is not equal to zero. So I will say that there are charges. And if the potential also come out to be zero, then I can very quickly say that there are no charges here in this room. So I will rule out the possibility of any charge only in that situation, and not to decide only on the electric field. Is electric potential obeying the superposition principle? So yes, electric field, just like when we write forces, electric forces, it is obeying the superposition principle, like many charges here. So there are different forces, and we can apply the superposition principle in order to calculate the total or the net force. Similarly, the electric field, which is the force per unit charge, this is also obeying the superposition principle, E1 plus E2 plus E3 and so on. Now these are vector in nature. So what about the electric potential? Whether the electric potential is also obeying the superposition principle? So yes, it is also obeying the superposition principle. V equals V1 plus V2 plus V3 and so on. So the potential, the superposition principle is obeyed by the potential as well. And about the unit of potential, I can say that from here I can write this thing in more simpler form, that E is equal to minus gradient of V. Then the minus, I know that it is due to the reference, that who is doing this work. So I can remove this minus and I can write in magnitude form here, this one minus, with no minus sign, gradient of V are in one dimension. I can write that this is equal to dV over dx. And if I remove it from this one, then means when the field, the potential, the field is uniform, then I can write that E is basically, as we write in capacitors, V over length. The electric potential or the potential per unit length. And here we know that electric field, from this definition, that F equals QE, then I can write that E is basically in the units of Newton per Coulomb. And I can write from here that this is Newton per Coulomb. So Newton per Coulomb, and when this L will be multiplied with this one, so meter will come in here, and this is equal to Newton into meter is joule per coulomb, and the joule per coulomb is defined as volt. So the unit of potential is volt. 1 volt is 1 joule per coulomb or 1 Newton meter per coulomb. Later on we will define, when we will be in electrodynamics, I will define the volt in terms of ampere as well, which is the unit of current. But for the moment we will go on only with this, that the unit of electric potential is volt. And in short, we denote it by V.